So we are here. Oh, yes, let's do the share. Doop. We're here to talk about frames, just a little bit about me and on to the actual subject at hand. Frames are like the fundamental building block of how everything gets transferred over Wi-Fi. So starting with, I saw the word block and I thought of, you'll see. Wi-Fi is complex. It's extremely complex. I started in this 25 years ago, and though the fundamentals haven't changed, it just keeps getting more and more complex with additional layers. And it's invisible as well. My children growing up, they ask, "What does your dad do?" And they're like, "He plays with invisible things, because we can't we have no way of interacting with our bodies and Wi-Fi. So we have to use tools to help us do that. But one of the great things about Wi-Fi, and it's also one of its downfalls, it's really resilient. So how are we going to explain how all this works? Well, of course, we're going to start with Legos because I saw the word block and then, fundamental building blocks. So you have to go to Legos. So when you start with Lego, it's it, it, it's just a mess. When you have information and you don't have it organized, it could be pretty, but it's just kind of a mess. But if we take that same amount of just lots of stuff and we organize it, all of a sudden it starts to make a little more sense. In this sense, I organize this all by color. And that's one way we can look at our data with Wi-Fi is we can do it. We can look at them at the frames by frame type. And that's kind of what we're going to talk about today. Another thing we can do with our same Legos is we can put them into not just by color, but by size and shape and get counts of everything. But where it really gets back together isn't that we just take the individual components and we organize them in ways. If we can turn it into a story, then it starts to mean something. We put it all together and it's like, oh, that's what all those little pieces were supposed to be. And yes, I did get these Legos and I did spread them all out and I made a little picture. So, hey, it gave me an excuse to have to get some more Legos. And then one of my granddaughters has this now. So let's start with the beginning. In Wi-Fi, we have three main types of frames. For those of you who've been around Ethernet for a while, Ethernet just has one. If you've been around for a long time, like back to Novell days, there were some other types, but normally we just have data frames only in Ethernet. In Wi-Fi, we have three types of frames: control, management, and data. And I don't know why I always say them in that order. It's actually management, control, and data. They're numbered, and when you look in Wireshark, you can actually see those numbers, and we'll see that in a minute. Management, control, and data. The only ones that can cross the threshold from wireless to wired are the data frames. The other frames, the management and control, have to do with getting on and off the network. That's management frames. How do you join a network? How do you get off the network? How do you find the next one to join? And control frames and controls are more like start and stop bits when we were doing serial. They're controlling the flow of data. So we have flow control frames, we have management frames for getting on and off, and then we have data frames themselves. And only the data frames can go over that boundary that an access point does that takes the wireless and converts it over to wired. And so the wired are the data frames, the rest stay on the wireless side. So if we look at them, there's a bunch of types here, and I color coded them with a color code that we've been using for a long time. It's also available in a from MetaGeek. That's who came up with this the first time around. And the industries, we kind of use these. And if you look, there's different types of management frames. There's association request, association response, probe request, probe response, beacons, DOS, deassociations. Those are all frames that have to do with getting on and off the network. Management frames. Control frames are, is it my turn to send, RTS? You're clear to send, CTS? Or for every single data frame, there's an ACK that comes after, meaning I sent you a frame, and if you acknowledged it, then I know that you got it. Part of this is all built because originally Wi-Fi, and it's actually still today, 802.11, we don't have any control over what happens. There isn't a central cell tower that knows who's talking when. It's all distributed. In fact, it's called a distributed coordination function. The coordination is not done by any one device or individual. Everyone shares it between themselves. So the protocol was made so that the protocol itself could coordinate between all the devices, even though no one device was in charge. Thus, we have these three types of frames: control, management, and data. And of data frames, we have mostly just data frames, but there's some unique ones. If we add QoS, then we have a QoS data frame. There's also a little baby data frame called a null data frame when we send a data frame with no payload at all. Now, this can also be very useful because if I send a null data frame, it doesn't have to take any payload. It doesn't waste any time sending payload, but it will be acknowledged. Management frames, control frames aren't normally acknowledged, but data frames are, so we can use that little null data frame as a kind of a trickster to let us do some other things. But all this starts down at the physical layer, down at the PHY. And if we look at it with a spectrum analyzer, we can see we could actually see the RF in the air. And those pieces at the beginning, the preamble, header, they're all part of the PLPC header, have to do with how the radio waves are used to start the beginning of a frame. Now, we're not going to get into all the details of PLPC headers and how every little bit counts. One, I used to think it mattered, but since I have no control over it, the people who are writing the Wi-Fi drivers, probably not even the driver guys, it's down to the chip guys who are the only ones who can adjust these functions. So though we may see them and may know how they're documented, as practitioners, we don't have any way to get in and touch these or change these. So in the RF frequency, in the medium, there's a bunch of things that have to happen, and these happen for every single frame that's going by. There is a lot of information that's in the air. Is the channel busy? Is it my turn to talk? Is there jitter, latency, multipath? All of these issues, regulation domain. Where are we in the world? What frequencies can we use and how can we use them? And all of this is happening dynamically all the time. But as practitioners, we have no ability to touch this at all. We can't change it. It just happens. But knowing how it happens will help us better design and troubleshoot and maintain our networks. So it starts with this. I have a frame that I want to send. And so before I can send it, and this doesn't matter if I'm a transmitter, it's a client transmitting or an AP transmitting, they have to go through this little contention process. This is part of that distributed coordination that if every device plays the same game, then they can get in and access the medium. It's not efficient, unlike LTE or other cellular technologies where there's some big boss in the cell tower telling people when to talk, and you have a time slice and you have to do with a certain coding. Here, it's all up to the individual device. It will wait and make sure that there's an empty channel, and if there's not an empty channel, it will continue to wait until it hears one, and then it will kind of roll the dice and pull a number. And if it gets the lowest number and it counts down to 0 and it's still nobody's transmitting on the medium, then it gets a chance and it transmits on the medium. And this happens for every single transmission in Wi-Fi. Now, these are happening down at the microsecond level, really, really fast, millionths of a second level. But the process, and we've in teaching this for years, we just call it the game, because every device has to kind of take this random walk to figure out, is it my turn to talk? If they pull it, they get to talk, they send out a signal, everyone else stops talking and allows them to finish, and then the process happens again for the next transmission. Now, that's all at the RF layer, the PHY layer. How it works, we're going to move up a layer up to the MAC layer, and behind the purple PHY layer, we have a MAC layer header, and it has things like frame control. I'm going to talk a bit about that in a second. It has addresses, 1, 2, 3, 4 addresses, which is kind of weird because in Ethernet we only have source and destination. But here we have source and destination, but we also have transmitter and receiver. Sometimes those can be repeated. Sometimes we'll use only 3. Sometimes we'll use 4 addresses if we're in a bridge mode. And then we transmit the payload itself. And then there's a little frame check sequence and a little buffer at the end. And that's how we send one frame in the air. Now, the only thing that's going to get converted from wireless 802.11 to wired 802.1 Ethernet is the network data, the payload itself. It will become an Ethernet frame when it comes out of the access point. Yeah, I'm not going to go into all this for you, but just realize every one of these little bits inside the header has value. It's telling all of the receivers, everyone who hears this, what I'm sending, when I'm sending it, who I'm sending it from, who it's it to. Am I the transmitter and the source, or am I just passing this on? So an access point will say, oh, the source is someplace upstream, but I'm going to transmit it. So the source address is some server, but the transmitter address is the access point itself. And then it puts them in these individual spots. Those spots are called DS bits, from DS and to DS. I was at a WICO conference a week or so ago, and someone was talking about this subject, but they didn't use this terminology. And anyone who's been through the CWNA should recognize this, because you really need to know how this process works. And the presenter was talking about a situation where he found these three addresses and didn't know what the fourth one was. The one time we use the fourth address is when we're in a wireless bridge mode, and that's the only time it happens. So just so you know, you should learn these. If I'm the first time ever showing you a to DS and a from DS bit, go study. This is just a quick review of that. So those DS bits will tell us who's the transmitter, who's the receiver, who's the source, and who's the destination. And those four pieces of information are useful as we're sending this frame along. Is it going to go from wireless to wired, or wired to wireless, or wireless to wireless? All of those need to be tagged, and they go along with this frame as it's being transmitted. Now, before we transmit the actual payload itself, we have to determine how are we going to modulate that frame. And this is why I love MCS so much, because it is self-reporting. The transmitter, doesn't matter if it's an access point or a client, the transmitter is going to sense in the air, not only instantly right now, but historically, what was I doing before? Did it work? Should I try something different? So the transmitter is going to look and say, I need to set a modulation technique. I need to set a coding scheme. I need to use a certain channel width. I need to set a guard interval. I need to transmit on a number, 1, 2, 3, 4 spatial streams, and I need to set my transmit power. All of those have to be decided before the payload itself is converted from ones and zeros into radio waves. All of that process is called the MCS, the management encoding scheme. And the table looks something like this. A client, if it's going to transmit, will first, before it even starts transmitting, it will go through in its association process and negotiate with the access point and say, I can do these things on this table. You can do these things on the table. How about if we agree on a subset and we'll stay within that subset? And then depending on the last frame I sent, if I sent it using a certain modulation scheme, a certain spatial streams, a certain channel width, transmit power, all those things, and you received it, you would send me an ACK. Now I know that you know that we sent the data and I used the right way. It worked. If, on the other hand, I use one of these MCS rates, coded it a certain way, sent it, and you didn't receive it properly, you couldn't decode it, you will not acknowledge. And now me as the transmitter, I have to determine, oh, which thing should I fix? Should I fix the modulation or the coding or the channel width or the guard interval or the spatial streams or my transmit power? One of those or multiple of those are what caused it not to work. So I'll have to try again. So as a client goes through, I say client, but the access point is a transmitter as well. It also has to do this for every single transmission it sends. It finds the certain combination of all these things that continues to work. And so one of the ways we can look at the health of our network is to see what MCSs are being used and are they consistent. That means that the RF medium is being happy. It's doing what it's supposed to do. So the higher the MCS rate are possible, and we stay in those MCS rates, then we know that our RF's doing well. Then we get to the actual data itself. We're going to send that MAC header. We're going to take the data and going to use whatever modulation scheme we wanted, and we'll send it out with a little frame check sequence. It goes over the air and the receiver gets it. If it all worked, they send back a hack, and we have completed one frame. Yay. Now, that's a nice setup of how this happens. But let's talk about the amount of time. We were looking at bits and DS bits, to from bits, all of the little individual bits that go on. We talked about how they happen in the radio waves. Let's now talk about how this protocol actually works in real time. So we've converted all those things that have to happen, both the radio ones, the MAC layer ones, the PHY ones, the MAC header, our payload, all of that together. And now let's look what happens is we send one single frame over the air. And this time we're looking at it based on time. So in the little graphics you see there, time is the horizontal axis. So in order to transmit a frame, we're going to have a AFS, this arbitration interframe space. It's the dead air. We're waiting for, is it my turn to talk? There's a little contention window of time to say, is anyone talking? No? Okay. Then I win that game. I'm going to send a preamble. The preamble is going to be formatted with the BPSK modulation. Then I'm going to send out a RTS, and the RTS is sent in the minimum basic rate. Then there is a CIFS as I'm waiting for that RTS to end where it's going, and that's a fixed amount of time based on it's fixed based on if I'm AC or AX. Each category has a unique one. Then there's another preamble. That preamble is also sent in BSK. Then the CTS comes back also at the MBR. Then there's another fixed CIFS. Then I now have permission to transmit. So I'm going to send my data frame. I will send out a preamble in BPSK. I will send out a preamble in VHT if we're in AC or above. I will send out a header, and that's sent in the minimum basic rate. And then my payload is going to go at the PHY rate that we negotiated in that MCS cycle. Then there's a little CRC that I'm going to throw at the end, a frame check sequence. Then there's a CIFS time, another specific time, and then there's a preamble, and finally the ACK is sent. So in order to transmit one data frame, all of these little steps have to take place. Yeah, like I said, it's complex. And here we are just going, yeah, the Wi-Fi works. The Wi-Fi sucks. It's terrible. It's good. But the magic is all these things are happening all of the time. I didn't want to just focus on this time. I wanted to focus and have you look at the size of the time. Depending on what we're doing, whether or not we're sending a 3,000 byte frame, the one on the upper right, or a 90 byte frame, all of the components, the non-blue colors, are fixed. They're just time, and they're based on whatever system we've set up. If we're AC, they're fixed on AC times. And the only thing that changes is that payload size. Now, in the top right, it's saying we're using the same data rate. So we negotiated MCS the same. And the only thing we changed was the payload itself. 3,000 bytes or 90 bytes. You can see, obviously, the 3,000 bytes is longer. It takes more time. But they both take way more time as a percentage. The data itself is a small piece of what actually goes on. The second scenario is just another thing we can look at. Same thing, airtime, but whether or not we changed our minimum basic rate, because those things will be changing based on MBR. One more view of this is if we look at the processes that take place. The first is arbitration. Is it my turn to talk? Can I get on the network? That takes almost 40% of the time to deliver one single frame. Then if we're running RTS CTS to clear the channel, make sure no one else is there, that takes about a quarter of the time. The payload itself is about a quarter. And then the ACK at the end is about 15%. The payload is the smallest piece. And if you actually look at the real payload, just the blue part itself, it's hardly anything at all. And Wi-Fi just takes a lot of time. So when people say, well, Wi-Fi is so inefficient, we should be using cellular, they're right. Wi-Fi is really inefficient. That's the way it works. But it works. It's cheap. The chips don't have to pay any huge amount to some cell manufacturer for their protocol. It's in fact, the chips are less than $1 a piece to get a Wi-Fi chip. The protocol is free. The frequency itself is unlicensed and free. So yeah, there's an overhead cost here, but it works. Now, one of those examples I showed was 90 byte frames versus 3000 byte frames. And we know it's more efficient if we use really big fat frames, because if we have a big payload as a ratio compared to the header and the trailer behind it, then it's more efficient. But in reality, and this comes from HPE Aruba, or maybe today I should say HPE Aruba Juniper Mist, kind of put them all together. They did some data, and on their networks, they found over 80% of the frames are tiny, tiny frames. And this is because the way the Ethernet protocol up above has things like TCP ACKs. And to send a TCP ACK for every TCP data frame, well, when you transmit that over wireless, it's going to be a little baby frame. And it's going to have its own preamble and its own CTS, RTS, and its own payload and its own CIFS ACK at the end, just to deliver this tiny little payload of TCP. So we are in the world where we send lots and lots of little bitty frames. So though Wi-Fi is resilient, it can recover amazingly. It's also really, really complex, as we've shown today. So when you compare those payload sizes, look at the total time. The total time to deliver a big frame versus the total time to deliver a small frame. And this is also comparing a data rate of 24 meg versus a data rate of 6 meg. A slow big one takes more time, but not that much more time. So a lot of times we get our customers who are like, I want to go to 160 meg or 320 meg channels because there's more data. The actual data itself, yes, the blue part's bigger, but we don't have anything we can do today to change all the other colors. That's just the 802.11 protocol. It has a lot of overhead. So even though we say we can send super, super fast data frames, we're still stuck that preamble is going out at BPSK because that's the way the protocol is written. So this was just a quick review of from PHY to the MAC layer to how we negotiate in MCSs to a view of what it takes to send a single data frame through the network. One last one here is just showing if we do nothing but change the data rate. This is 300 meg data rate versus 86 meg data rate. And note the amount of time saved is very, very little. But the actual speed test result that you'd receive would show, oh, look at where it'd be like 3 times faster. And yet the amount of time in the air didn't change any. Now, time for a little quiz. Since we missed the quiz earlier, I'm going to just ask a simple question. We have control, management, and data frames. 3 different types of frames. What if, and I'll just play a what if here, and you're going to play along as the audience. What if I had a third management frames, a third data frames, and a third control frames? What could you tell me about the network itself? Is my Wi-Fi happy? Do, 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 do. Hold that thought. Now let's compare it to another one. Let's say I have 90% management frames and only 5% data and 5% control. Now, what do you think about that Wi-Fi? Is it happy? Is it sad? Is RF good? Is RF bad? Hold that one in your head. And the last one, what if I had, let's say, 20% management, 20% data. No, I'll change this one. 20% management, 20% control, and 60% data. So 3 datas for every 1 control and for every 1 management. You've been thinking? Okay, let's go back and look at each of these. If I'm running and I have management frames, remember, management frames are those that have to do with getting on and off the network. That includes beacons, and beacons go out. Each beacon goes out 10 times per second per SSID per radio. They chatter a lot. Plus, all of the probe requests, probe responses, and every time an AP hears a probe request, it has to send a probe response. Those chatter. Every time a client wants to associate or disassociate or get on and off or roam, those are management frames. So if I had the one that was 90% management frames and only 5% data and control, nothing at all wrong with that network. That tells me the network is doing exactly what it's supposed to be doing when the network is idle at 2 in the morning. As a percentage, the only thing that's really happening is beacon, beacon, beacon all day long. It's happening all night long. So yes, if I have lots and lots of management frames and a small amount of control and data, but the control and data are equal, that tells me the network is actually very happy. Because every time I send a data frame, I want to send a control frame. Data ACK, data ACK. And then let's go to the last one. I have 20% management, 20% control, and 60% data. You would think, look, we're sending lots and lots of data. But what that tells me is I'm sending data, no ACK, data, no ACK, data, ACK. Management frames are just going to happen anyway, but looking at the ratio of data to control is going to tell me about how healthy my network is. If I see more data than controls, I know that I have retries, because that means the data was sent and it didn't get an ACK, so I had to send the data again. I don't like seeing more data than controls. Let's say I see 3 controls for every data. Now I'm doing RTS, CTS, data ACK. That's 3 controls for every data. Now that tells me I have a protection mode on. So even if all you have are simple ratios of control management data to each other, you can do a pretty decent job of troubleshooting your network. Now, how do we bring order from all this chaos? There's lots and lots of Lego pieces just laying around. When you turn on Wireshark and you're looking at all of this data just flowing by, it's a little confusing. So one thing we can do is apply a color filter. And now we know management's one color, controls one color, data's another color, and that helps. But we also built in Wireshark, there's a way to have filters, and a filter will allow you to filter down on certain things. And there's lots and lots of filters you can apply in Wireshark. So Fernay and I put together a profile that we use in Wireshark, and it has these little drop-down buttons: management, control, data. And under management, you just drop this button down and say, show me all the authentication requests. And it has pre-built the filter for authentication requests, so I don't have to remember what that looks like. If I want to find just my MAC address, I can go into one of the data frames and put in a MAC address for me. If I want to look at control frames or all data frames that are smaller than 1,500 bytes, we have those filters already built. And on the right side, we have some additional ones that we might be looking for some health of the network. So if you're tired of looking at this, it's easy to be able to drill down and learn a little more by having pre-canned filters for you. Well, that's what I had prepared for today, to try to help you understand all the little frame issues that happen inside of Wi-Fi. But now we get to hear from Eric on 7 Minutes with 7 Signal.
Hey.
But
Right.
if we have some questions first, I'll see if I can answer those for you.
Let's do that, Keith. That was awesome stuff. Before we get into questions, 2 things that you said that I just want to clue in on, and that is, it's a miracle it works. It's really remarkable.
It is shocking. Yes.
It's shocking. And yeah, I think just kind of embellishing in that appreciation is perfectly normal and certainly acceptable. And the other thing is like, wow, I mean, we have to go through all of this rigmarole. Why? Well, it's free. Okay, so the two things that I really took away were, wow, it is complicated and it's a miracle it works. And guys, it's free. It's available to us. We don't have to pay the FCC. We don't have to get some kind of specific, we don't have to pay for some kind of proprietary anything. It's all made available to us. And I just have like this gratitude as you were talking. So it's really remarkable. Okay, let's get into some questions here. First question. And two are kind of, it's how do 802.11ax frames compare to 802.11n and 802.11ac frames? Are there differences that you can kind of tell or see or in the behavior or
Yeah. So there's multiple places we can look at that. During the association process, a AC client or an AX client or even a BE client that we have now
Mhm.
will, in its request, it will say, I can do these things. How about you? And the access point responds and says, well, I can do these things. And then they react and they agree on a subset of those things. So we didn't even talk about the complexity if you add MIMO and multi-user MIMO. I mean, there's even more complex things. I just started with the basics and they're already complex enough. So a frame will say those things. And in the header, it hasn't changed in 25 years, the basics in the MAC layer header. But what they've done, and this is kind of the beauty of it, it's kind of like the US Constitution. It was made with the thought in mind it's going to get amendments later on.
Right.
And so 802.11 was originally written, and they said, we don't know where this is going to go in the future, but let's build a structure that it could adapt in the future. And so every couple of years, we have new amendments come out to add new features. Those questions were, how can you tell which features are there? They've
Mhm.
been added in those amendments. So there's some things in a beacon frame that add additional information elements that say I can do these new things. So on this last slide here, some of the little ones on the right side, we added between G, A, and N and AC. You can ask it different questions. And so there's a filter that will filter against that payload, the actual data frame itself, and say, find one that meets this criteria. And the reason that they're different is because they're different criteria. So we have a very specific filter to get a B data rate versus a G data rate versus a and whether or not which QAM they're using. So
And so, and then along those lines, we shouldn't have to worry when they come out with Wi-Fi 8 because it'll be an amendment. And those
yes,
amendments, and you could just look at the headers, you can just look at the frames, and you should be able to see that it's identified as such, and that it has these capabilities. And when you say capabilities, Keith, you mean like data rate supported and things like that?
yeah, data rate supported, spatial speeds supported.
Supported.
The original 802.11 didn't even have a country code in it. That came out later. So even which country, which geography you're in, and today that's a pretty big issue, as in you could be in a different country and your client isn't in Norway, but you are in Norway, and yet the AP can't do something, but your client
Right.
can.
Yep.
And so while you're in Norway, your client has to obey Norwegian rules, and it
Right.
does. And
Okay.
yet that was never in the original 802.11, but it was an amendment, and now clients continue to do it. So they're both backward compatible and forward compatible.
hmm Wow, that's amazing. All right, good stuff. Good stuff. Well, let me see if there's any other questions here before we get going here. Okay, here's one more. Here's one more. Let's see. Does IEEE have any expectations of trying to increase the data rate of the overhead to increase the frame rate, to increase the throughput? Sort of like the greenfield mode with 802.11n through 2009.
I remembered that it was going to be beautiful. It was going
Was?
to save so much. And we had this whole new greenfield thought and it just died. Uh, and it wasn't even a glorious death. It just died because it didn't work. We had a chance. And now this question, like whoever asked it, is totally my pet peeve. And so I'm gonna go off a little bit here.
Okay.
We could have stopped being backward compatible, and that's the reason we haven't changed, is we have to be backward compatible. And we're
Right.
still backward compatible all the way to 802.11 prime, even before B came out. We could have when we moved to 6 gig. The reason the greenfield didn't work for N
Mhm.
was we were still using the same frequencies. And if I was a true greenfield and there was no old things there and I turned it on, it could go faster than if there was any old stuff there. But if I even heard a little teeny snippet from a neighbor who still had the old stuff, I
Yeah.
had to downgrade. So the result was, especially in 2.4, we I built greenfield places, a brand new warehouse. There was nothing in it, but it would hear a neighbor and it would just downgrade back to what it was anyway. So it didn't work. But we did have a chance when we got 6 gigahertz. There was nothing in 6 gigahertz that had to be backward compatible.
Nope.
We as the industry, but starting with the chip manufacturers, we could have changed how that whole overhead part worked. We could have made it more efficient. The chip manufacturers chose not to because it
Interesting.
was more expedient for them to not have to rewrite anything in their code, and they could just port it over to this with a 6 gig radio and everything worked the same.
Yeah.
So yes, we had a chance. We could have got rid of all sorts of that overhead, but that was the reason we could have at 6 gig. We didn't. The chip vendors didn't. So then everyone else followed, and no one else could. So
Right.
yeah, we could have, we didn't, and we're here now, and so we're backward compatible, and yet it
Yep.
still works.
Yeah, it's amazing. I mean, and a lot of people ask questions like, well, why can't we do certain things like cell carriers? And it's because of things like backwards compatibility, I mean, it is free, it's public. I mean, and so we're trying to accommodate as many people as possible. And
Even the
sometimes,
unlicensed bands. And the
yeah,
problem is we have this unlicensed band that we're actually in all unlicensed bands, we're sharing it with other technologies.
that's right.
Wi-Fi isn't the only one using 5 gig or 2.4.
Right.
So we have to play nice, and yeah, it's sad. I went through some angst when the 6 gig happened and I didn't get what I wanted,
Yeah.
but
Yeah.
it
Now,
is
when
what
you
it
say
is.
the chip manufacturers, you mean like Intel and Qualcomm?
Broadcom, Qualcomm, they kind of got together and said, let's not reinvent the wheel now. It
Okay.
was a perfect time. They could have reinvented the wheel. And, but they're also the owners of the intellectual property of how the cell information works. And they sell those chips at a greater cost than Wi-Fi chips. So it was in their best interest to not make Wi-Fi that efficient.
Yeah, it always comes down to money. Okay, one more question. What are the preferred frames to check channel utilization? I normally look at beacons, but how reliable is this?
Uh, that is the access point itself answering it, and it is optional. Some vendors do not put in channel utilization in their beacons.
Mhm.
If they do, and you read it, uh, I'm not going to use the word trust here because it's one data point. You could, from your position, think of a client versus an access point. The access point says, as I'm transmitting this data in the air, I'm estimating how much airtime is available for me to transmit, and I'm going to turn that into a channel utilization, and I'm going to tell the world I'm really busy. I don't have a lot of free time to transmit. And then clients will hear that and can, or I could have a client sitting listening to the channel and seeing how much channel utilization is actually being used and how much is left over.
Right.
My position of where I'm sitting or where my sensor is sitting will see something different than the access point sees from its position. So they're both reporting what they see, but they're in two different places. So just realize the beacon saying, from my point of view, this is what I see, but a sensor reports something different, and a client will report something even different than that. It's not it's not unuseful. It's terribly useful. I use it all the time.
Mhm.
What I'd like seeing more than channel utilization is the MCS rates that the clients are sending and what the AP is sending. Because if I have a low channel utilization, but my MCS rates for my AP are really low, then he might have a lot of time to transmit, because there's no one else talking. But when he does transmit, he has to transmit at a really low MCS. That means the
Mm,
RF has got a problem of some
yep.
kind. So,
Yeah.
so any one piece of data is useful, but when you put them all together, you get a better picture of what's going on.
Yep. Right on. Right on. Okay, guys. I think that does it. That is it's the perfect segue actually into our next segment, which of course is 7 minutes with Seven Signal, featuring me, where we take a little feature inside Seven Signal, unpack it, and show you how it can have huge value. Keith, this was awesome, and I am excited to show you some of what you've been talking about in Seven Signal right here, right now. So come on, let's go. I'm going to share my screen, and let's hit screen 2, and let's hit share. And everything's moving in slow motion, but give me the thumbs up, Keith, if you can see my screen. All right. Okay, guys, here we go. Here we go. Look at this. I mean, inside Seven Signal, I mean, we've got a frames tab right here. Let me show you what some of the capabilities are. This is totally cool. Actually, let me scroll down to the bottom and show you some of these things that we're measuring. Beacon channel utilization. Look at that. So Seven Signal is looking at all of the beacons on every single access point. And we're actually, like, you can mouse over this and you can see, wow, this access point in this location, 3.25% of the airtime is being taken up by beacons. All right. Now, 3%, big deal. 1%, big deal. But in some environments, that could be a big deal. And it's important to kind of see what's going on. You know this. We all know this. Some organizations, they've got, 3, 4, 5, 6 SSIDs, and they're all beaconing, and they're, all these different bands and all of these different SSIDs. It can add up. And so we want to be able to see that, and we can do that right here in Seven Signal. What else can we see on the frames tab? Let's take a look. Look at this. This is in frames per minute, the probe response density on a channel. And you could mouse over this and you can actually see, wow, this access point, this sensor, this is what it's seeing on this channel with regards to frames per minute. What else can we see? Let's keep going a little bit here. Here's probe request channel utilization. So we're not only getting the frames per minute, but we're also getting a rate or a percentage of utilization. So you can see here that probe requests itty bitty, teeny tiny in terms of how much airtime is actually being used. Probe response, a little bit of a different story. And I'll tell you what, guys, 4%, you go to Madison Square Garden, that's nothing. You look at the probe responses in an arena, and it is like crazy, reaching the rafters, if you will. And organizations have to be able to see that in order so that they can make different adjustments. Now, granted, you go into your controller and there's these different thresholds that you can set in order to ignore all of that stuff. And you have to do that. Otherwise, the air would just be overwhelmed with all of these probe responses. It can get really ugly. Let's keep going. Uplink data, downlink data, data volume. Okay, now let's keep going here. I wanted to get to one, right? Okay, so here's the QBSS channel utilization that's being broadcast. And you can see how high this percentage is right here. Pretty crazy. And to Keith's point a moment ago, he said, look, it's trying to do the best it can and, and all of that. And that's why at Seven Signal, we do our own airtime utilization calculation, which is right here, total airtime utilization, where we're actually, we do our own little packet captures and our own little sniffs, and we're actually looking at all of the frames, and we're actually coming up with our own estimation, our own calculation. And usually it meets QBSS channel utilization from your controller pretty well, but sometimes it doesn't, so it's important to have that, and that's why we calculate it ourselves. Now, we were talking about Wi-Fi 5 and Wi-Fi 6 a moment ago. Yes, in Seven Signal, you can actually see OFDMA airtime utilization. And here you can see total is 0. We're breaking it up into upload OFDMA and download OFDMA. So, and these percentages are so small, it's really just kind of coming back as 0. Look at this, guys. 0.09%, just fractions of a percent. But what it does is it kind of allows us to see if OFDMA, if Wi-Fi 6 is in effect in our environment. There were a lot of promises. Wi-Fi 6, OFDMA, it's going to allow this channel sharing technology. Are we even taking advantage of it? Is it actually even being used? Do we have clients in our environment? Is this actually helping? And so now you can actually see if, in fact, it's helping because you can see how it's utilized or not in your environment. Let's keep going. Let's keep going. So now we're looking at airtime utilization. Let's keep going. Let's keep going. Frame size, client frame size in bytes. Multi-use, so right here, now we're looking at retries, multi-user retries, which is your OFDMA, versus just regular old single-user client retries. So just like Keith said, we're looking at those retransmission frames. How many are there? Okay, and then what's the percentage of them compared to all of the frames that are in the air? And that's how we come up with a retry rate in 7 Signal, as you can see right here, 20%, 25%. All Wi-Fi networks have retries, but we try to guess this, it's just the nature of the protocol. If it doesn't get through, let's retry. But if we can keep the retry rate below 30%, then we're going to be just fine. It starts climbing into the 30s, 40s, 50s, just like Keith said. Whoa, this is a noisy environment. And, maybe we need to do some remediation. Now, the second thing that I wanted to show you that Keith was talking about were those data rates and those MCSs, because the MCS is like a tremendous score that really helps you with identifying the health and wellness of clients in your environment and how they're interacting with the RF. So let's slip on over to the data rates tab right here and let me show you what we got. So here's an example, okay, in this Los Angeles area on this access point. These are the MAC addresses. So as you can see over here, guys, when we do our little sniffs, we're getting the OUIs and we're getting the MAC addresses of every single client that we can hear that's connected to each and every access point. And you can see those all right here. Okay, when you see Intel corporate, I want you to think of your Dell and your Lenovo laptops. Okay, when you see unknown, then that's usually an Android device at Android 11 or a Mac OS that's scrambled its MacBook or that scrambled its MAC address. Okay, down here you can see, and here's Apple. So maybe these are some older Apples where the MAC address, the OUI is not scrambled and we can tell what they are. I'll tell you what though, sometimes you see really cool stuff in here in terms of all of the clients that are using Wi-Fi in our environment. Just like Keith said, this is public. You can do anything you want. All sorts of people have written all sorts of different things to work. This AMPAC technology, you might say to yourself, what is that? I don't understand. So what do? You go over here and you look up AMPAC and you see, oh, wow, okay. Industrial devices, smart speakers, IP cameras, tablets. Oh yeah, okay. That's that AV equipment that we have over in the corner now. Now I know what that is. And what's its health and wellness? Can we infer what the experience is? Well, of course we can, because we can see its MCS right here. And so you can see right here, and I can mouse over these little bars right here, and it's going to reveal the IP or the MAC address of that device. If I can get it, come on. I might have to zoom in. There we go. And when I do that, I can mouse over this little guy right here, and it should tell me what the MAC address is. Maybe not lucky today. That's fine. But I can see that over here correlating to the color, and it actually enables me to see, okay, is this device actually performing well or poorly on my network? Honestly, when I see a lot of devices at this MCS of 4, 5, 6, I'm like, wow, what's going on in the environment? I really would hope to see more of like a 6, 7, 8, depending upon, the data rates that I expect out of my environment. But it's here for you. The data rates telling you the health and wellness of different kinds of devices connected to access points. And not only that, but right here in 7 Signal, the frames. And if I were to just show you a quick list of all of the different options that we have available to you in 7 Signal, let's go to expand all and check it out. Okay. Our sensor is gathering everything, and a lot of people knock 7 Signal. Hey, Eric, you guys have too much information. But I'll tell you what, guys, when it comes to solving tough problems, you're going to be glad you had this information and these metrics and statistics and measurements at your disposal. I mean, it just
I
keeps
don't know
going
if I
on.
don't know if you can have too much information because it's a computer. You have filters. You can filter it out.
Thank you, Keith. I appreciate that greatly, because it's true. The data is there for you. We try to have a good default set of parameters that kind of show you just the basics. And I can show you that right here. If we were to go to the basic KPI list, these are the basic things that we try to show people. But look at everything else that's available to you. everything that you need in order to solve tough problems. So that's what I wanted to share with you guys today. This has been fun. I love these tech talks with you, Keith. Always learn something new, and I appreciate it. And I just wanted to remind you and everybody else out there listening today, thank you for coming. And just remember that while you and me, we can't see or hear Wi-Fi, it's invisible, but 7 Signal can. So thanks for joining us, everybody. Really appreciate it. And I hope you had fun today. We'll see you next time.
Bye.